The intensity map here provides a visual representation of the intensity of a given peak in the spectrum as a function of the analysed position. The map is titled with the element name and wavelength of the reference peak selected for mapping, and the spectrum number to which it relates. Changing the element or spectrum to map will update the map with the corresponding data. So if we change the spectrum number to map to 2, the map's updated accordingly, and if we change the element selected to say calcium, the map is again updated. We'll just reset those values. The reference peak mapped can be changed in the element identification configuration window. It's this value here. So currently we're mapping 341.476 nanometers, but we can update that to one of the other reference peaks for nickel, say 344.626, and the map will be updated accordingly. The peak intensity at each measurement location is marked using a coloured circular dot. The diameter of this dot marker corresponds to the crater diameter specified in the mapping configuration. So if we look at the mapping configuration, the crater diameter is set to 0.5 millimeters. But again, this is just an indicative value that's set by the user. And it's up to the user to select an appropriate value. The colour of each marker is defined by the scale to the right of the map here. A number of values are specified with the scale, and these are as follows. SM is the spectrum maximum, the maximum intensity in the currently selected spectrum number. PM is the peak maximum, the maximum intensity of the currently selected peak in the currently selected spectrum number. UL, or upper limit, the intensity corresponding to the upper end of the colour scale, indicated by the blue colour. LL, the lower limit, the intensity corresponding to the lower end of the colour scale, red, down here. SM here is spectrum minimum, the minimum intensity in the currently selected spectrum number. And PM is the peak minimum, the minimum intensity of the currently selected peak in the currently selected spectrum number. So this gives an idea of the range of intensities in the spectrum as a whole and for the specific peak that has been mapped. The spectrum and peak range values can be used to provide important information about the peak in the spectrum. For example, if the spectrum maximum value, SM here, is say 60,000 and the peak maximum value is around 100, then it is clear that the intensity of the selected peak is very low and probably close to noise levels. In addition, if the peak maximum, PM, and the peak minimum values are similar, the variability of the intensity at different locations is unlikely to be due to changes in the composition of the sample at different analysis positions, but to the intrinsic variability of the LIBS measurement. For example, if we look at an intensity map for the silver peak at 243.778 nanometers, so if we select silver and the peak at 243.778 nanometers, and also in spectrum 1, the peak maximum and peak minimum values here and here are of the same order of magnitude, indicating that the variability in this map is just due to spectral noise. However, if we look at the intensity map for the zinc peak at 330.258 nanometers, so select zinc and we have 330.258, the peak maximum value here is of the same order of magnitude as the spectrum maximum value, while the value of peak minimum here is 2 orders of magnitude lower. This map clearly indicates that zinc is more abundant on the right-hand side of the sample than on the left. The upper limit value of the scale is initially set equal to the peak maximum value. So we can see UL and PM are set to the same values. And the lower limit is set equal to the peak minimum value. So lower limit LL is the same as the peak minimum value. However, the scale limits can be edited by the user within the limits of the spectrum intensity range, and doing so can sometimes enhance the map to more clearly distinguish the presence of an element. So for example, we could edit the lower limit to be, say, 3.5 E4 and the upper limit to be 1 E5, and we can see that the colour scale is updated in the map, and doing this can enhance certain features. When the user changes the spectrum number to map value to display results for a different spectrum, the upper limit and lower limit values are updated automatically based on the new data. So if we change to spectrum number 2, we can see the upper limit and lower limit have been automatically updated to match the data displayed. However, the lock intensity range option can be enabled on the configuration screen to fix these values if required. So if we enable this checkbox here, then when we change the spectrum number to map, the upper limit and lower limit remain fixed. This can sometimes be useful when comparing the mapped intensities for different spectra. Note that the information provided by the identification map and the intensity map is complementary. The identification maps provide information on the presence of a given element, while the intensity maps provide an indication of the abundance of an element. Note also that while the identification algorithm employs several emission lines to confirm the presence of an element, the intensity map is created using a single emission line, and therefore attention should be paid to possible interferences with emission lines of other elements. If we look at spectrum 1 for zinc, we can see an example of the complementary nature of the information provided in the identification and intensity maps. In the identification map, zinc is indicated as being present throughout the whole of the analysed area of the sample. Whereas in the intensity map, we can see that the concentration of zinc is indicated as being higher on the right-hand side of the sample than on the left.